This is part 1 of Module 14, our module on transformers. Let's begin with a review of magnetic induction. Supposing we had a coil with n turns, and we let a current I flow through the coil. The current I will cause a magnetic field to be produced in the vicinity of the coil. If this magnetic field is varying with time, that is, dphi by dt is not equal to 0, the changing magnetic field will induce a voltage E across the coil. And from Faraday's law, we know that E is equal to N dphi by dt, where N is the number of turns of the coil. We have also learned that E is equal to L di dt, where L is called the inductance of the coil. Supposing we wind a coil around a core. So this is our core. It is made of a low reluctance material. Now, what do we mean by reluctance? Reluctance is the tendency of a material to resist the flow of magnetic flux. It is analogous to resistance, which is the tendency of a material to resist the flow of electric current. You have reluctance in magnetic circuits, analogous to resistance in electric circuits. If we connect a source across the coil, expect a current I to flow. Whenever you have a current flowing through a coil, expect a magnetic flux to be produced. Because the core has very low reluctance, the flux will tend to confine itself to the core. In other words, very little of the flux will leak into the atmosphere. If dphi by dt is not equal to 0, then a voltage will be induced across the coil. Now suppose we wind another coil around the same core. The second coil will experience the same flux that the first coil is experiencing. Therefore, a voltage should also be induced across the second coil. Note that when nothing is connected to coil 2, so nothing is connected here, the current that will flow in coil 1, I1, will be equal to the magnetizing current. This is the current required for magnetic flux to flow in the core. The lower the reluctance of the core, the smaller the required magnetizing current. In other words, when nothing is connected to coil 2, I1 will be quite small. From Faraday's law, we know that E1, the voltage across coil 1, is equal to N1 dphi by dt. E2 will be equal to N2, the number of turns of coil 2, multiplied by the same dphi by dt, because it is the same flux flowing through coil 1 and coil 2. Thus, E1 over E2 will equal N1 over N2. Suppose now we connect a load across coil 2. The induced voltage across E2 will cause a current to flow through the load. Now, what will be the result of this current flowing through the load? The consequence of this current flowing through the load would be for the coil 2 to produce a flux that is opposing the original flux. So there will be an opposing flux. So the tendency is for the total flux in the core to be reduced. However, I1 will automatically increase so that the flow of flux in the core is sustained. In other words, I1 will no longer be just the magnetizing current. I1 will also contain a component that will allow a current I2 to flow in the load. Let's define a new quantity, MMF or magnetomotive force. Magnetomotive force is associated with a coil carrying a current I. Magnetomotive force is equal to the number of turns times the current, and this is measured in ampere turns. MMF in a magnetic circuit is analogous to EMF in an electric circuit, EMF or electromotive force. MMF is the force that pushes flux to flow in a magnetic circuit, whereas EMF is the force that pushes current to flow in an electric circuit. EMF, by the way, has the unit volts. MMF at N1 must be balanced by the MMF at N2. In an electric circuit, the corresponding rule is the EMF encountered as you traverse a closed path is equal to 0, which is Kirchhoff's voltage law. So if N1 I1 is equal to N2 I2, then you have the relationship I1 over I2 should equal to N2 over N1. This, by the way, is the structure of a basic two-winding transformer. So in summary, a basic transformer has two windings sharing a common core. The windings have N1 turns and N2 turns respectively. We say the turns ratio is N1 is to N2. The winding where the source connects is referred to as the primary winding, and the winding where the load connects is referred to as the secondary winding. For an ideal transformer, the AC voltages and AC currents will be related as follows, and this we earlier derived. E1 over E2 is equal to N1 over N2, and I1 over I2 is equal to N2 over N1. Note that N1 and N2 are real numbers. Therefore, E1 over E2 will also be a real number. Or E1 and E2 will be in phase. Same thing with I1 and I2. They will be in phase. Now, the phase angle between E1 and I1 will not necessarily be 0. The above relationships apply to the time domain expressions for your voltages and currents. But they also apply to amplitudes, effective values, and phasor values. So for example, instead of time domain E1 over time domain E2, you can have E1 RMS over E2 RMS. This is N1 over N2. So it will apply to the RMS value of the voltages. Or I1 phasor over I2 phasor is equal to N2 over N1. The current relationship will apply to phasor values. Let me now test your understanding of what has just been discussed. So you purchased a 100 volt appliance from Japan. Unfortunately, you only have 230 volts in your home. To convert from 230 volts to 100 volts, you decide to wind your own transformer. By the way, when voltages are expressed in this manner, we are assuming these are RMS values. So if you have 1,000 turns in the secondary, how many turns are required in the primary? So let's compute that. Okay, we have E1 is equal to 230 volts. This is RMS. This is our primary voltage. E2 is equal to 100 volts. This is our secondary voltage. We don't know what N1 is, or we're trying to figure out what N1 we need. N2 is 1,000 turns. So we know that E1 over E2 should equal to N1 over N2. Thus, N1 should be equal to N2, which is 1,000, multiplied by E1, that's 230, over E2, which is 100. So we're going to get 2,300 turns. So when we wind the primary winding, we would need 2,300 turns. Okay, second part of the question. The current drawn by the appliance should not exceed 10 amperes. You wish to place a fuse in series with the primary winding to protect both the transformer and appliance. So you're trying to protect both the transformer and appliance in case there is an overload. What should the rating of the fuse be? So let's try to illustrate this situation. So we have a transformer. Your secondary is connected to an appliance. So you have a current I2 flowing through that appliance. Then you have a primary. This is connected to your source through a fuse. So this is a fuse. So this is I1. What you want to happen is, if I2 exceeds 10 amperes, you want the fuse to blow, thus disconnecting the source from the transformer. So we already know that the turns ratio, N1 over N2, is going to be 2,300 is to 1,000. Okay, so I1 over I2 is equal to N2 over N1. Okay. At I2 equal to 10 amperes, I1 will be equal to 10. Okay, this is equal to I2 multiplied by 1,000 over 2,300. Okay, and that's going to give you 4.3 amperes. So the fuse that we connect should be 4.3 amperes, so that when I2 exceeds 10 amperes, the fuse is going to blow. Let's discuss transformer ratings before we move further. This is typically found on a nameplate mounted on the transformer. What type of information do you expect to find? Well, first, it will give you the volt ampere rating. This is the maximum allowable volt ampere or kilovolt ampere. So recall that volt ampere is equal to E RMS multiplied by I RMS. The RMS values of the voltage and current multiplied together. So this is either the primary or secondary. The rated voltages are the voltages for which the transformer was designed. So for the previous example, the rated voltages are 230 volts at the primary and 100 volts at the secondary. And you call that a step-down transformer. When the primary has a lower voltage than the secondary, then you call it a step-up transformer. The rated currents are the maximum allowable currents that you allow to flow in the windings. So you have a maximum current for your high voltage side and a maximum current for your low voltage side. If you take the rated voltage and the rated current together for any particular side, that should be consistent with the volt ampere rating of your transformer. And then you might find some other information on the nameplate. For example, you will commonly find information on how much loss there is in your transformer. In this case, that would be the energy lost in the core plus the energy lost in the windings. So here's an example of what a nameplate rating or nameplate would look like. So as you can see, you have their volts information, current information, and you have loss information, plus a number of other items that is not of interest at this moment for us. So again, let me test your understanding of transformer ratings. Supposing I had a single phase transformer, okay, single phase, no, don't mind that term for the moment, no. So supposing I had a transformer which is the following nameplate data. It has a volt ampere rating of 50 kVA, and then the high voltage side voltage is 7620 and the low voltage side voltage is 230. Transformers are usually, how do you say it? No? A transformer, usually, you can use either side to be the primary or the secondary. In other words, if I were to use this as a step-down transformer, I would apply a voltage at the high voltage side, no? And then my load would be at the low voltage side. I can also use this as a step-up transformer. I apply a voltage 230 volts at the low voltage side. I'm going to get a voltage 7620 at the high voltage side. So determine the high voltage side and low voltage side currents if operating at rated kVA. So meaning to say it's operating at 50 kVA with 230 volts applied to the low voltage side. So this means I'm using it as a step-up transformer. Okay. If I have 230 volts applied to the low voltage side, my E, high voltage, will be equal to 7620. Because that is exactly the rating of the transformer. So my high voltage side current will be equal to my kVA, which is 50,000, divided by 7620, which will give me 6.56 amperes. And my low voltage side current will be 50,000, that is my kVA rating, divided by my low voltage side voltage, which is 230. So I'm going to get 217.4 amperes. Let's make it a little bit more interesting. Determine the high voltage side and low voltage side currents if operating at half its rated kVA, so meaning it's operating at 25 kVA, with 7,500 volts applied to the high voltage side. Now, even if the transformer was designed for 7620, that will not stop you from applying a different voltage. As long as it's near the rated voltage, the transformer should operate fine. It will follow the turns ratio it was designed for. So the first thing we do is, let's compute what the low voltage side voltage is going to be. No? So E high voltage over E low voltage is equal to 7620 over 230. No? This is the turns ratio is the same as the voltage ratio. So I can compute for my E low voltage, which will be equal to 7,500 multiplied by 230 divided by 7620. So I'm going to get 226.4 volts. No? Notice my high voltage is slightly less than 7620. So my low voltage side voltage will also be slightly less than 230 volts. What is going to be my high voltage current? That's going to be my kVA at which it is operating, 25,000 divided by 7,500. So this is 3.33 amperes. And my low voltage side current will be 25,000 divided by 226.4, which will give me 110.4 amperes. So I hope this is clear. Let's now define what an ideal transformer really is. Because remember, the relationship E1 over E2 equal to N1 over N2 and I1 over I2 equal to N2 over N1 only applies to an ideal transformer. If your transformer is ideal, then we assume, number one, that coils 1 and 2 have zero resistance. So you can see why we're saying it's ideal. It's impossible for a coil to have zero resistance. If you unravel a coil of 1,000 turns, you know how long that's going to be. And you know that the longer the conductor, the greater the resistance. Okay? But we assume it is ideal and that it has zero resistance. Number two, no leakage flux in coils 1 and 2. Whatever flux produced at the primary will be felt at the secondary. There will be no flux lost. Number three, no heat loss in the core. I don't know if any of you have experience with transformers in your homes. Maybe you might have a 110 volt appliance which was bought for the US, which you're using your 220 volt supply. Even if there's nothing connected to your transformer, if you plug it in, you're going to feel that the core is hot. So there will be heat loss in the core. Finally, for an ideal transformer, we assume that the permeability of the core is infinite. Permeability is inversely proportional to reluctance. So remember I mentioned that reluctance is the tendency of a material to resist the flow of flux. So it's the tendency of the core to resist the flow of flux. And permeability is inversely proportional to reluctance. In an electric circuit, resistance is analogous to reluctance, and conductivity is analogous to permeability. So if the permeability is infinite, then that means the exciting current is zero. How do we define again exciting current? That is the current that will flow when there is no load, when this is taken out. So with no load, in an ideal transformer, I1 will be equal to 0. These are the possible circuit representations of transformers. This is the more general representation. showing the primary and secondary, the turns ratio. So you have the turns ratio here. Okay. This representation implies that it is an iron core. So this implies that it is an iron core transformer. Okay. A transformer may not have an iron core. No? It may have a different material for its core. In fact, there are transformers that have air core. No? The magnetic coupling is through the air, but it is impossible for such a transformer to be treated as ideal. It will be far from ideal. Notice we have two dots here and two dots here. We call those our dot markings. And this indicate the relative polarity of E1 with respect to E2. This is dictated by the direction in which the coils are wound around the core. In other words, if I have this dot marking, say this dot and this dot, okay, if this is E1, then my E2 is going to have this polarity, E2. Okay. That is dictated by the direction in which the coils are wound around the core. So here's an example. Here, the coil is wound around the core in the clockwise direction. Okay. You can imagine it from top to bottom. The wire is being wound around the core in the clockwise direction. And here, it is being wound in the counterclockwise direction. Okay, so if this is clockwise direction, this is counterclockwise direction, then this will be your dot markings, or this will be your relative polarities, E1 and E2. On the other hand, okay, again here I have clockwise, and here I also have clockwise. Then my dot marking is going to be, this is dotted with this. So these are going to be my relative polarities. This is E1 and this is E2. Let's now study the analysis of circuits that contain transformers. So here is a simple circuit that contains a transformer. I have a source that is connected to a load through a transformer. If I get the phasor equivalent of the circuit above, it is going to come out like this. Notice that all the time domain expressions have been converted to their equivalent phasors. We've already shown that for an ideal transformer, E1 over E2 phasor values is equal to N1 over N2, and I1 over I2 phasor values is equal to N2 over N1. If I solve for E1 and I1 from these expressions, this is what I'm going to get. No? I'm going to get E1 is equal to N1 over N2 E2, and I1 is equal to N2 over N1 I2. Now let J equivalent be the equivalent impedance seen by the source V sub S. In other words, J equivalent is the impedance seen by V sub S at its terminals. Okay. J equivalent would be equal to V sub S divided by I1. But V sub S over I1 is just E1 over I1. And if I substitute these quantities into that expression, I'm going to get J equivalent is equal to N1 over N2 squared E2 over I2. So I wrote that again here. Note that E2 over I2 is the load voltage divided by the load current, which should equal the load impedance. Thus, Z equivalent is N1 over N2 squared multiplied by the load impedance. What is the significance of this derivation? It means that if I have a circuit such as this, that is equivalent to this simplified circuit. From the perspective of the source, whether it is Z equivalent connected or this transformer circuit connected, the source will feel exactly the same thing, which is the essence of equivalence. In this case, we say the load impedance has been referred from the secondary to the primary. So we had an impedance at the secondary. We transferred it to the primary using this formula, and we are now able to get rid of the transformer. So let's show an example of how this can be used. So I have a transformer with a turns ratio of 1000:100. I have a source whose RMS value is equal to 220 volts. If Z of L is 4 plus J3 ohms, so this is Z of L, what is the RMS value of the source current? So my solution, I will refer Z of L to the primary, and I will call it ZL prime. ZL prime will just be N1 over N2 squared multiplied by Z of L. N1 over N2 is 10, so I will have 100 times Z of L, or 400 plus J 300. So this is now my equivalent circuit. Note that it's now easy for me using phasor computation to determine the value of I of S. In this case, V of S has not been assigned an angle. Since we're only interested in the RMS value of I of S, we can make V of S our reference phasor. So let V of S be our reference phasor. So that means V of S is equal to 220 at an angle 0 degrees volts. I of S now, the phasor I of S, is just V of S over ZL prime. So this is equal to 220 at an angle 0 degrees divided by 400 plus J 300, which will give me, from my calculator, 0.44 at minus 36.87 degrees amperes. So from what I know about phasors, this is my RMS value. So IS, the RMS value of the phasor I of S, is equal to 0.44. Note that this is an acceptable notation for the magnitude of this phasor, or by definition, its RMS value. So let's continue with circuit analysis with transformers. So we previously derived these two expressions. Okay. Let me now multiply the first expression with the conjugate of I1. I1 conjugate from this expression will just be equal to N2 over N1 multiplied by I2 conjugate. Okay? So if I multiply this by this and simplify, I'm going to get this relationship. But what is E1 I1 conjugate? That is P1 plus JQ1. And E2I2 conjugate is P2 plus J Q2. So what are we saying here? Whatever the power and reactive power generated at the source will be totally transferred to the load. No? The transformer is not going to get any of it. Whatever is generated will be transferred. The power and reactive power delivered by the source are the power and reactive power received by the load. The transformer does not absorb any real or reactive power. Okay. So let's have a second example. Find the power and reactive power supplied by the source. The transformer turns ratio is 2:1. I have a load impedance Z of L, which is 8 plus J6. I have an impedance connected to the secondary, in series with the secondary, and impedance in series with the primary. And my source voltage is just given by its RMS value. So my solution. What I'm going to do is I'm going to refer these two impedances, Z2 and ZL, to the primary. So let Z2 prime and ZL prime be Z2 and ZL referred to the primary. Okay, so what is Z2 prime? Z2 prime is just N1 over N2 squared multiplied by Z2. So this is 2 squared 4 multiplied by Z2. I'm going to get 1.2 plus J 1.6 ohms. Okay. And ZL prime is N1 over N2 squared multiplied by ZL, which will give me 32 plus J 24 ohms. So this is now my equivalent circuit. Notice ZL prime and Z2 prime were referred to the primary, and I can now get rid of the transformer. And so now I can compute for I of S. So again, we let V of S be our reference phasor. So V of S is equal to 220 at an angle 0 degrees volts. So I of S is V of S over Z1 plus Z2 prime plus ZL prime. So this is equal to 220 at an angle 0 degrees over 1.6 plus J 1.2 plus 1.2 plus J 1.6 plus 32 plus J 24. And using your calculators, you'll come up with the result 5.01 at an angle minus 37.60 degrees amperes. Okay, but the problem is, what are the power and reactive power delivered by the source? Well, I know the voltage, I know the current supplied by the source. Okay, I can use the complex power relationship. The power supplied by the source, the complex power supplied by the source, is just V of S, I of S conjugate. So this is 220 at an angle 0 degrees multiplied by 5.01 at an angle of, the conjugate of I of S would be, the angle would be 37.60 degrees. And using my calculator, this will be 873 plus J 672.3. Okay, what are the units for S? This is volt amperes. From complex power, we know that this is P of S, and we know that this is Q of S. Thus, P of S is 873 watts, and Q sub S is 672.3 vars. Okay, an alternative solution is to refer impedance Z1 and the voltage source V sub S to the secondary side. So, instead of referring these to the primary, we will refer these two to the secondary. Okay. So, what is Z1 prime? This is Z1 referred to the secondary. This is N2 over N1 squared. Note now, it's N2 over N1 because we're going from the primary to the secondary, multiplied by Z1. Okay. So this is going to be Z1 divided by 4, or 0.4 plus J 0.3 ohms. Okay, what about V sub S prime? V sub S prime will just be governed by the turns ratio relationship. So V sub S prime is N2 over N1 multiplied by V sub S. So this will be 110 at an angle 0 degrees volts. So now we can easily solve for I sub L. I sub L is V sub S prime over Z1 prime plus Z2 plus Z sub L. Okay, so this is 110 at an angle 0 over 0.4 plus J 0.3 plus 0.3 plus J 0.4 plus 8 plus J 6. And voila, from your calculator, you're going to get 10.02 at an angle minus 37.6 degrees amperes. So what are the power and reactive power delivered by V sub S prime? Let's call that S of S prime, complex power. This is V sub S prime multiplied by I sub L conjugate. So this is 110 at an angle 0 degrees multiplied by 10.02. So conjugate, so this is 37.60 degrees. And from your calculator, I'm going to get 873 plus J 672.3. This is volt amperes. Okay, this is P sub S prime, and this is Q sub S prime. But remember, the transformer does not absorb any real or reactive power. Therefore, P sub S should equal P sub S prime, and Q sub S should equal Q sub S prime. In other words, even if it had been referred to the secondary, whatever power and reactive power it will be delivering would have been the same power and reactive power it would have delivered if it was still in the primary. Okay? So we have the same answer. No? P sub S is 873 watts and Q sub S is 672.3 vars. Let's have a third example. The load L consumes 1 kilowatt at 0.85 power factor lag. What are the real and reactive power delivered by the source? Assume the transformers are ideal. Okay, let's form the power triangle of the load. So this is the power triangle of the load. The base would be 1000 watts, that's P sub L. The angle would be R cosine of 0.85. The height would be Q sub L. And we also know that the diagonal would be S of L. So the nice thing about the power triangle, if you know any two quantities, you can determine all other quantities. So from the power triangle, I can get Q's of L. Q's of L is just piece of L multiplied by the tangent of the arc cosine of 0.85, which will give me 619.7 vars. Okay, again, remember, whatever power and reactive power generated here will just transfer all the way to the load. No? This is not going to take up any of it, and this is not going to take up any of it because T1 and T2 are ideal. No? Therefore, piece of S must equal to piece of L, and Q's of S must equal to Q's of L. No? So piece of S will be 1000, and Q's of S would be 619.7 vars. In the solution of this problem, we didn't even have to know what the load voltage was. You need to know the load voltage to compute for the load current, but we didn't have to compute for the load current. Okay? And we didn't also have to know what the transformer turns ratios were. As long as they're ideal, whatever was generated here, okay, will be transferred all the way to the load. Okay, here's another example. The load L consumes 1 kilowatt at 0.95 power factor lead. It is supplied through a transformer with 2080 turns at the source side and 1010 turns at the load side. So this is 2080 and this is 110. So it's a step-down transformer. The source voltage is adjusted so that the load voltage, V sub L, is maintained at 220 volts RMS. So the problem is to find the amplitude of the source current, the source current I sub S. Here is my proposed solution outline. Using the power triangle, I can determine the RMS value of the load current, which is I sub L. And then since I know the turns ratio, I can now determine the RMS value of the source current. And then I convert from RMS value to amplitude. So note that there is no need for phasors. No? We can work with RMS values. Okay, how do I get the RMS value of my load current? From the power triangle, I can compute for S of L. S of L is piece of L over my power factor of the load, which is 1000 divided by 0.95, which will give me 1052.6 volt amperes. But we know that S of L, which is the apparent power, is the load RMS value times the load current RMS value. Thus, I sub L would just be S of L over V sub L, which is 1052.6 divided by 220, and I'm going to get 4.78 amperes. Okay? So that took care of step 1. No? So this is my step 1. My step 2, using the turns ratio, I compute now for the RMS value of I sub S. So I sub S is N2 over N1 multiplied by I sub L, which is 110 over 2080 multiplied by 4.78, and I'm going to get 0.253 amperes. Okay, so what is step 3? I know that the time domain expression for my i's of s of t will be the square root of 2 multiplied by 0.253. Okay. So I'm now doing a reverse phasor transformation. No? Cosine of omega t, I don't know what omega is, plus a certain alpha which I don't know. No? But I'm really only interested in this because this is my amplitude. Okay? Thus, my amplitude will be square root of 2 multiplied by 0.253. This is 0.358 amperes. So that's the answer. The amplitude of i's of s of t is 0.358 amperes. So that's the end of part 1 of your module on transformers. In part 2, we will be taking up more examples. Thank you.